Dear students, till the lecture 15 we have gone through main information regarding analysis and design of beams and we have gone through singly reinforced beam as well as doubly reinforced beam. So how to do the analysis and what are the various provisions or guidelines which we have to take into consideration based on IS 456 2000 and according to that information, whatever we have labeled in the code which is relevant, we have already designed various type of sections, that is beam section, rectangular type of section, and singly reinforced, doubly reinforced. So all the detail we have gone through in the previous lectures, theoretical as well as guideline and the various steps which we have to follow in the design, as well as we have also gone through actual design problem of singly reinforced beam as well as doubly reinforced beam. So today we are going to discuss the guidelines as well as all the type of information which is required in case of flange type of beams. So now let us go through the theory part first of all, that means definition part. Reinforced concrete floors. So when you are going to construct any beam or any slab or any type of RCC structure, that any type of building, industrial building, residential building, whatever. So generally we have to design reinforced concrete floor system, and in which you will be finding that you have to design the beams, columns as well as slabs. So when we are talking about the floor system, so then floor mean that we have to discuss and we mean by slabs. So there may be various type of slabs, and that slab will be supported by beams, so which we have gone through, and which are often casted monolithically. So you may be observing that we are discussing all type of beams and later on slabs, and their design will be individual design we are going to discuss, that is design of beam and design of slab. But when you observe during construction, most of the time you will find that slab and beam, they are cast monolithical, not as a separate element but as a composite type of element. However, if they are not cast monolithically, then even some kind of shear connector we have to provide, so that they should act as a composite section. So whatever the load coming on the beam, ultimately that has to be transferred to the columns, but on the beam load will be coming from the slabs. There may be dead load, live load, or any type of other type of loads. So we are expecting that whatever the loads, effect of loads, any type of stresses or bending moment, and that beam and slab, if they just share the load as a composite member, then it will be much better in case of any type of RCC type of structure. Now beam and slabs are so casted that they should act together as a composite section, as I told, so that they can easily resist external loads. Now due to this, we can consider that some portion of the slab is to be considered to act as together with the beam. So we can say that beam as well as some portion of the slab which is on the beam, they should be acting as a composite section. In these cases, we can say that beam have some extra width at the top, and those extra width at the top, that we can consider, and it is termed as flanges. So that means on beam, that component of the slab which we can consider, and that is known as flange, and they result into the formation of T-shaped beam. That means the beam which will be just resembling the English word T. So that alphabet T accordingly. So its shape will be just like T. That's why they are called as T-beams. And the part of T-beam below the slab is referred as web or stem, and the component of the slab which is acting as the component part of the T-beam, so that will be called as flange. So that means T-beam consists of flange at the top, and below the flange, that is below the slab, the portion of the beam will be considered as a web, or you can call it as a stem. Now beams may be L-shaped also. That means if you find the end of the slab, and that beam connected at the end of the slab, so then it will be looking like alphabet L. So that will be termed as L shape. So both type of whether T beam or whether it is L beam, they are termed as flange type of sections. So from this diagram we can easily understand that you can observe that this is a slab which is supported by three number of beams. You can say that it is a in here you can say it is a continuation. So we are taking this is the end of the slab, and this end of the slab is supported by a beam, so that this portion, if I highlight this portion of the slab as well as beam, they resemble like just as alphabet L, so we can say it is a T beam. And similarly, this blue color section which you can see, it is just like alphabet T. So this type of beam will be termed as a T beam. So as already we have discussed that this portion of the slab which we have to consider, that this portion of the slab is just acting as a part of the, you can say, beam. So that means this much portion as this much portion, this whole blue color diagram which I have shown, so it is a T beam basically. And this portion, vertical portion, is known as web, and the topmost portion, that is the part of the slab, it is known as flange. And similarly this is also a T beam. So you can see in this diagram one L beam is shown and two T beams are shown. Now same diagram will be referred throughout the lecture. So that means this is L beam, T beam, flange, web, and it is slab. Now stirrups, when you are providing stirrups in the web, that means reinforcement in the web. So whatever the stirrup you are providing, you can extend those stirrups into the slab, so that they further make the beam and slab act together. So ultimately when we are providing stirrups, suppose stirrup like here, so this stirrup will be extended to the slab. So ultimately this portion of the slab which is termed as flange, as well as the portion of the beam which is termed as web, they will act as a one component composite section. So that's why we will term it as a T beam. Now when the flange of the width, when the flange width is larger, so that means this flange width, we can say this is the width of the flange. So when flange width is larger, then the flexural compressive stress is not uniform over its width, and the stress varies from a maximum value in the web region to progressively lower value at the point farther away from the web. That means if you draw the stress diagram, then the stress diagram will not be uniform if your width of the flange is sufficiently larger. Now here what we have to assume, we are assuming that a uniform stress distribution will be across the width of the section for simplicity, otherwise it will not be difficult to analyze the section. So this is our assumption that however the stress, compressive stress will be varying with the width, but for the analysis part and design part we have to just consider it as a uniform stress distribution. The entire rectangular portion of the beam, this portion of the beam, other than overhanging part of the flange. So that means we can consider this portion of the beam, and this left side and right side, they are the overhanging part of the flange, is considered at the shear web in the shear calculation. So that means when you have to do any type of shear calculation, then whole portion of this beam, which is vertical portion, you can say, so that will be considered as web, and the other portion of the flange which is extended, or you can say it is a overhanging portion, so that will be considered as overhanging portion only. For T-beam, the flange on the both side of web, that means this is flange as well as this is flange on the both side of web, and the effective flange width. Now it is just an hypothetical value. That means what will be the effective width of the flange as per IS code. So we will be taken into consideration the guidelines given in IS 456 for design and calculation purpose. So what we want to say, that how much portion of the slab will be considered as a flange, so that as per the codal guideline we will call it as effective width. So if this is suppose 500 mm, then maybe effective width may be lesser or greater than this, so that we have to work out, and accordingly we have to follow the guidelines. So similarly now, if you see here the analysis part, then T-beam is just similar to rectangular beam. You can consider this whole beam as a, suppose this is a rectangular beam like this whole portion you can consider as a rectangular beam, and this much portion you can remove from it, or it can be deducted. So ultimately this T-beam section is just similar to the rectangular type of beam. So same type of methodology we can adopt in analysis as well as design of the T-beam. So this information we have discussed so far. Now as per IS 456, so what is the information available in IS 456 regarding the T-beam or L-beam? So we have to refer this clause number 23.1. Now let us see what information is available in clause 23.1. So first of all, very basic information is a slab which is assumed to act as a compression flange of the T-beam or L-beam should satisfy the following condition. So that means the slab which is on the beam, it can only be considered as a part of the beam, or so that they can act as a T-beam. You can design it as a T-beam, you can do the analysis as a T-beam only if these conditions are satisfied. So first of all, the slab shall be casted integrally with the web. So that means they should be cast monolithically, or we can say another condition, the web and the slab shall be effectively bonded together in any other manner. And the second condition is, if the main reinforcement of slab is parallel to the beam, then transverse reinforcement shall be provided as in figure number 3. Now you can refer this figure number 3 in IS 456. So for this information, this definition part or this condition, you have to refer clause number 23.1. So this information is available in IS 456. So such that reinforcement shall not be less than 60% of the main reinforcement at mid-span of the slab. So what you have to take into consideration, if the slab and the beam which you are going to construct, if they are satisfying these two requirements as mentioned by code, then you can consider that portion of the some portion of the slab as connected to the beam, and now you need not to design them separately. You can design them as a composite section, and the new name of that beam will be T-beam. And if it is at the end of the slab, then as already I have told you that you have to consider it as a L-beam section. Now from this diagram it is very much clear, and you can see this slab is supported by three beams. It is extended, that means it is a continuous type of slab, but we have taken this diagram so that we can understand what is the meaning of effective flange, what is T beam, what is L beam, etc. Now if you consider that this slab as well as these beam, their construction is satisfying the condition as mentioned in IS 456, then what we can consider? We can consider that some portion of the slab, as per the information, as per the formula which code is mentioning, and this much portion of the slab you can consider is a part of this beam only. So that means this beam as well as this portion of the slab you can just design as a single component, as a composite section. Similarly, here at the end you can consider this portion of the beam as well as this slab. They will act as a composite section, and that will be termed as L section. So first of all, let us understand how to get the value of effective flange of the any T-beam section. So what portion of, that means what width of the slab above the web or above the beam we can consider as effective flange. So here you can see that S1 is the center to center, that means span length, center to center span length between these two beams, as well as suppose S2 is center to center span length of these two beams. So S1 and S2, they may have a same value, that means similar span length can be there. Now if let us talk about this T section. So this portion is known as, already told you that this is a web and this is flange. So this means this slab, if you cut from here, this slab is considered as the flange of this T beam. And from this topmost fiber, as I have told, as we have taken in any singly reinforced type of section, if this is steel, so this distance we consider as effective depth. So that means top of the flange, distance from top of flange to the center of the reinforcement in the web portion, that will be effective depth of the this T beam section. And VW is the width of the web. So web as well as web. Now here what you have to take into consideration as per code, effective width of the flange should not be greater than S1 plus S2 by 2. And if this is the flange, then this will be the depth of the flange. Capital DF is the depth of the flange, VW is the width of flange web, and small d is the effective depth of the this beam section. Similar terminology we can use here, and the information is available in IS 456. So what is VF here? VF is the effective width of the flange, VW is width of the web of the beam, DF, capital DF is the thickness of the flange, or you can say depth of the flange or depth of the thickness of the slab, and small v, which we are considering, which is actual width of the flange, and that means actual width of the flange. So you have to take into consideration that your actual width of flange should not be greater than effective width of the flange. Okay, now here we have to consider that effective width of flange you can calculate as per clause 23.1.2, and effective width of flange section can be taken for design calculation as per the formulas given below. Now for T-beam section, what should be the effective width of flange? So this formula, you have to take the least value of these two equations. That means this is first equation as well as this is the second equation. L naught by 6 plus BW plus 6 times DF, or BW plus S naught. Now what is L naught? L naught is the distance between the point of contraflexure, which is known as zero moment, or effective span for simply spotted beam. If it is a simply spotted beam, what should be the effective span? And 0.7 times the effective span for the continuous type of beam. So this will be the L0 value based on different type of conditions. So you have to just work out the value, that is L0 by 6 plus BW plus 6DF, or whichever the least value that will be acting as a, that is the effective width of the flange. And similarly for L beam you have to consider this equation, and this equation is available in IS 456. So from that you can refer. So this is L0 by 12 plus BW plus 3TF, or BW plus S0. What is S0? S0 is the half the sum of the clear distance to the adjacent beam on either side. So there may be adjacent beams, accordingly you have to take into consideration. And if there is an isolated T beam, so here I mentioned that isolated beam mean when the slab is discontinuous at the sides. So then you have to refer this formula, and if it is a isolated L beam, then we have to refer this formula. So based on the different type of conditions, as per codal provision clause number 23.1.2, we can easily work out what should be the effective width of the flange. Now analysis of flange section. So basic assumption which we have discussed, that basic assumption state that in for rectangular section are applicable to this section also. Whatever the basic assumptions which we have taken into consideration while analyzing and designing rectangular sections, so same type of assumptions are applicable here also. So depending upon the magnitude of the applied bending moment, so how much bending moment is coming on the section, accordingly neutral axis will be shifting, or neutral axis may be below the flange or it may be within the flange. That means you can say neutral axis may lie within the flange or outside flange. So we have different cases. Accordingly, we have to decide what should be the effect of the uh, applied bending moment. Now, first case which we can consider, that if the neutral axis lies within the flange, so that means then depth of neutral axis will be definitely less than width of thickness of the flange or depth of the flange. So this type of diagram you can easily understand that this is a T-beam section, and this dotted line indicate the position or location of the neutral axis. So you can easily understand that in this case neutral axis is lying within the flange, where xu is the depth of neutral axis, capital DF is the depth of the flange or thickness of the flange, and here it is a singly reinforced type of section. This is the reinforcement which we have shown in the web, and VW is the width of the web, and small d is the effective depth of this section, and BF, as we have already discussed, it is the width of the flange section. So what you will be observing here, stress and strain diagram, if you see, so stress epsilon st will be the stress strain at the level of the reinforcement, and accordingly what you have to see here, you have to take into consideration, that means this will be the distance d minus xu, because whole is distance is d. So this is the depth of neutral xu. So from this up to the center of the reinforcement, this distance will be d minus xu. Now again, as we have discussed, the same methodology is applicable as was applicable in the rectangular type of section. So you can see strain in the outermost fiber of the concrete, that is compression fiber, it reaches 0.0035, and there is some variation in the stress diagram, and at the top it is again 0.447 as was in case of topmost compression fiber of rectangular section, that is 0.447 FCK. But here the diagram will be somewhat parabolic, that means some portion will be straight line and again other portion will be parabolic, and this steel will be touching its ultimate stress 0.87 Fy. Now in first case, as we have discussed, what will be the first point, you will be able to understand here that compression zone occupy only a part of the flange. So that means only this shaded portion will be the taking the compressive stresses, and below that it will not take any compressive stresses. That means we will be ignoring this portion. And as we have discussed, the concrete section in the flange below the neutral axis. So that means this much portion, no doubt there is a concrete, but we will be just ignoring this portion to take any type of compressive stresses. And the steel will be taking care of the tensile stresses. Now you can treat a beam, just a T-beam, as a rectangular type of beam, as we have discussed earlier. What is rectangular type? That means this will be a beam, rectangular type of beam you can consider. Now if this is a rectangular beam, then it is having a width is equal to BF and depth is equal to effective depth of the section. And so accordingly you can easily understand and very easily you can solve this type of numerical. Even you can solve, you can design, you can do the analysis part. So based on this information which we have discussed so far, you can easily calculate depth of the neutral axis as we have done in case of a rectangular beam, and accordingly you can find out moment of resistance of this section if the depth of the neutral axis is lesser than the depth of the flange. So this formula you can apply to get the moment of resistance of this T-beam section when neutral axis lies within the flange. Now second case is when the neutral axis lies outside the flange. So you can see here, this is the neutral axis. It is within the web portion, that means it is outside the flange, and this will be the depth of the neutral axis. Now at top level you can see that strain in the compression fiber at this level, top of the flange, it is 0.0035, and because at this level the width of the section is directly reduced from BF to BW. That means it is quite lesser than the width. So maximum strain which is acceptable at this level is 0.002, and the rest is same type of diagram, stress as well as strain. So what you can observe that this shaded portion, that means the shaded portion will be able to take the compressive stresses. So compressive zone occupies flange as well as some part of the web, and this information you can refer from the IS code. That means when this condition is fulfilled, 3xu by 7 is greater than or equal to df, and df is greater than or equal to 0.2d. So for more detailed information is out of scope of our syllabi, so that means I am not going into such detail. And if this condition is satisfied, this first condition is satisfied, then you can easily calculate moment of resistance of T section from Engg G, and you can refer clause G 2.2 of IS 456. And if this condition is meeting, your section is meeting this condition, and then you can refer subclause G 2.2.1 of IS 456. And a third condition, that means if XU max is greater than XU and greater than DF, then you have to follow guideline whatever we mentioned in G